How are we
Hi,
doing,
Sam.
Jay?
Yeah, good,
I'm
thanks. Yeah,
loving I'm loving the background, by the way. Way to go. Why not have the lesson at Anfield?
yeah, thanks.
Brilliant. Okay, how are we doing this morning?
Yeah, I'm good, thanks. Yeah, I'm good. I'm good.
Good stuff, good stuff. Okay. So I'm using a slightly different board today, Jay.
Yeah,
I'm using this whiteboard now. Are you able to see it okay?
yeah, yeah.
Okay, with the title
Uh,
Radioactivity, no problem. Okay, so this is just it's what do you call a mobby pad that I'm going to be using. It's just it might make life a little bit easier. Now, Jay, tell me something. Are you able to click a record button on your end as well for the session?
A record. Yeah, yeah.
Yeah,
Shall I click?
yeah, click
Okay.
that, and then you've got
It
the
says,
lesson that will be
please
recorded.
request record permission from the meeting host.
Okay, let's have a look then. Security maybe. Share screen, enable. Let's have a look here then. More. Right, video share. Right, okay. Not a problem. I just thought you would be able to, might have to go into settings. See
Yeah.
security, share screen, chat, rename, annotate. Right, it says request permission, it says.
Is that
If you
requested?
click that, yeah, if you click that, will it send me some kind of request?
Right, I'll click it now.
Try and see if
Just
that
clicked
sends
it.
me a request.
Has it sent it you? Sorry.
Just trying to see if I've gotten anything here. Let's just participants. Do I need to go into more maybe? Allow record. Yeah, there we go.
Yeah,
Okay.
now I can record. Yeah. Thanks.
Okay, so you can record the session now, can't you?
Yeah, yeah.
Excellent, excellent.
Yeah.
Okay, superb. So what I could do here, no, the more isn't helping me. No problems. Okay, so you can get the lesson. Now, I presume it will be saving it to your computer. So what you might want to do, Jay, is
Yeah.
perhaps even get an external hard drive, just because sometimes videos can take up a lot of space.
Yeah.
Alternatively, I'll see how this comes out in terms of a link. I'm trying to use another software here as well, which would
Mm-hmm.
then create a YouTube link for you, which means
Yeah.
then you don't have to save it on your computer. You can just you're going to have your own access, your own link on
Yeah.
YouTube to that video. So that's another way of doing it. You could also do it from your computer once you've finished recording and save it that way, just to save
Yeah.
you space on the computer. Okay, right. So radioactivity, that's our sort of main discussion today. Oops, didn't want that to happen. Let's move this up here. I'll move it to the corner, Jay. All right, now, no, no, this, I'm not even, something's gone wrong. It's not very good. All right, let me just take these off. I don't know why it's, okay, so we're gonna start off then with atomic structure then, Jay. Can you
Yeah.
just briefly remind me what you can remember, the small little things that you can remember about atomic structure? What comprises the atomic structure?
Or is it just so that in the atom there's a nucleus, protons,
Yep,
neutrons, and then so nucleus, protons, neutrons, and
yep,
that's pretty much electrons as well, negative.
okay. So So atomic, oops, I'm not so used to using this whiteboard, but I thought I'd try it out today. Anyway, atomic structure. So you're
Yeah,
right. We're saying that what we have is we've got a core, haven't we? Which we call the nucleus. And
yeah,
inside that core, we have things which we call neutrons. Okay, neutrons. I'm putting in two neutrons. And of course, we have these things known as protons. Okay.
yeah.
Now, can you tell me a little bit about what you know about protons?
Well,
And
protons they have a positive charge, one
good.
plus, and then neutrons they have a negative. No, they're neutral. Sorry, and electrons,
Neutrons, and
they're
absolutely
neutral.
correct. Yes, correct stuff. Okay, so we've got protons which are positively charged, and we've got neutrons which are negatively charged. So now, Jay, we know, or you probably remember from, and I'll just complete this diagram here. You recall though from learning about, oops, there we go. That's my circle. So it looks like a funny little person. You recall anyway from learning about electrostatics and charges, yeah,
Yeah.
that if I have a negative charge and I bring it next to a negative charge, what do I expect to see? So let's imagine I've got two
Oh,
things that are negatively charged. What would I expect to see?
won't they repel because they're both?
Yeah,
Yeah.
absolutely. They would repel, wouldn't they? So let's
Yeah.
think a little bit then about this structure of the atom. What's
Mhm.
unusual about the structure? You notice anything unusual about the structure of the atom?
Um, well, it's stable.
Okay, it's stable, yes, but there's something particularly unusual that is defying stability. Is there anything in there that you spot? And by the way, this is not a question you have on an exam, but it's just
Yeah.
to help you get a deeper understanding. So it's not an exam
Um,
question.
um,
So we've just said, and I'll just give you a little hint here. We've
yeah.
just said that positive, oops, plus positive repel.
Oh, yes.
Also
Yeah.
negative plus and negative, sorry,
Yeah.
also repel. So we know whenever
Mhm.
we've got a positive situation, a negative situation, we repel. Now, where do we have a positive situation in that atom?
With the positive and positive um, protons.
Absolutely, you're right. Yep. So these protons here, what's keeping them together? What's making
Would
them
it
not
be the
bounce off or run off
because
or split open?
no, not the electrons, sorry, because they're no, wait. Um, would it be the neutrons maybe? Because they haven't got.
Well, the neutrons actually have zero charge on them. So if they were negatively charged, we might have been able to say, oh, that's because they are attracted to the negative
Yeah,
neutrons, isn't it?
yeah.
Yeah. So what is it actually that's keeping them together and not making that nucleus split open?
One of the electrons that attract it towards them. So
Yeah, sort of. But an interesting fact here with regards to the size of the nucleus is actually very, very, very tiny. Oops, let me get a red pen. So this nucleus, okay, so nucleus, this is approximately equal to, oops, 1/10,000th. This is rubbish, really. I should have just used a visualizer. I think it would be
yeah.
much better. 1/10,000th of the diameter of an atom, okay?
Hmm.
Of an atom. So this is pretty dense, the
Yeah,
nucleus, and the electrons are pretty far away. So if you have to think about it on a scale, if you had a football field size, Anfield, we'll take it, and you had a pea size in the
yeah.
center of that stadium, that would represent the nucleus, and on the outside of the stadium would be where the first electrons would be found.
No, okay, so it's big, like
It's
well,
yes, there's a
small.
huge space. So it'd be
Yeah,
very hard to think of the protons as being attracted to the electrons, and that's why they're there. It's not
yeah,
an easy question, actually, this one. And I think a lot of students overlook the question when they first thought about the atom because it doesn't almost come intuitively. Now, in here, actually, in the nucleus, you've got something known as the strong nuclear force. Okay.
yeah,
It is actually a fundamental force of physics, strong nuclear force. Now, other forces that you've already encountered are things like gravitational force. Yeah.
Yeah.
This is a special type of force known as a strong nuclear force, and it only exists, it only acts over a very, very small distance. This distance here, oops, where's my cursor? Yeah, it only acts over a very small distance within the nucleus. So it's what keeps the protons from wanting to burst out of the
So the
nucleus.
strong nuclear force keeps them all together.
Absolutely,
Yeah.
absolutely. And actually, what happens is if you are building an atom, and I'll just change my screen to simulation, which might help matters here. New share, and we'll go to this here. Okay. So
Yeah.
there we go. We're building an atom. So what do? We can put some protons in the nucleus. It tells us instantly that this is identified as hydrogen because hydrogen has only one proton. There's no neutrons in hydrogen, by the way. Yeah. So I can put a few more things. Let's see. I'm going to click stable and then stable so that we can see whether we're creating something that is stable. Now here in this case, Jay, you can see that I have created what is known as an ion. It's just positively charged. Now, if I put an electron into the orbit, now I have a neutral atom. Now, there's nothing new there because you know that this positive has been neutralized by this negative. In other words, a +1 has added to a -1, giving us a net charge of 0. And we can have a look at the net charge here. We've got one single positive and a single negative. Now I add a neutron to this arrangement, okay? Still tells me it's still stable.
Yeah,
Okay,
because it's got
and it is
neutral.
still identifying it as a hydrogen atom. Yeah, still
Yeah.
identifying it as a hydrogen atom, even after I've added one neutron. Why is it still identifying it as a hydrogen atom?
Is it because it's still neutral, has the same charge, and it still has one proton and one neutron?
Still
Or
has
not
one
one
proton and
proton,
one
one
neutron,
electron.
okay? And the
Yeah.
key thing is that the identity of an atom is given by the number of protons,
Yeah.
okay? That is the key thing. If I added another proton here, I am no longer looking at hydrogen anymore, okay? So the
Yeah.
identity, remember, is given by the number of protons. So even when I add another neutron, now, okay, this is telling me something. It gets unstable. I've added another neutron. I've still got hydrogen.
Yeah.
What form or what version are all these different hydrogens? I had this hydrogen, that's still hydrogen. That's
Are they
also still
isotopes?
hydrogen. So why are all three, or what term do we call all these three different atoms of hydrogen that I have made?
Isotopes.
Well done, okay? So we say
Yeah.
that isotopes are atoms of the same element, all right? But they have different masses, okay? Now, this brings us into the idea of what we call mass number and atomic number of an atom. Can you recall what mass number is? And I'll just change my screen share to that there.
Is it the number of protons and neutrons, I think? Or,
Number of protons and neutrons. Sorry, let me just flick to the next page, okay? And we're gonna say, oops, we're gonna say atomic number. Okay, so atomic number first, Jay. Did you
yeah.
mention that it is the number of protons and neutrons?
Yeah.
Okay, that is not actually quite right. So the atomic number is simply the number of protons.
Right. Yeah.
Okay, number of protons. They're easily confused because of the terms are very alike almost. You've got mass number, then you've got atomic number. But the atomic number is simply the number of protons, okay? Now, the number of protons, remember, Jay, is the signature for that atom, which we just saw. We had the same hydrogen element or isotopes of hydrogen with the same number of protons. Therefore, it was still identified as hydrogen. So it is the signature. That's what the atomic number is. Therefore, it is given by the number of protons. All right. And this
Okay.
is normally given a particular symbol, which you will see. And this symbol is the symbol Z. Okay. So just be aware when you see a symbol Z, we are looking at the atomic number. Okay. Then you have also got this thing which we call the mass number. Okay, so you rightly mentioned, so mass number. Now this is given by the number of protons and neutrons. Okay.
Yeah.
And this is in effect saying, it's telling us how heavy that particular atom is. Now, protons and neutrons are significantly heavier than electrons. So electrons are near enough zero mass. So majority of the mass of an atom is actually comprised of the protons and neutrons, okay?
Yeah.
Now, this is given a certain symbol, and the symbol for this is A, okay? So
Yeah.
if you have an element, one of the notations you will come across, okay, is if I have an element X, there we go, in the periodic table, yeah, and if you're using a very good periodic table, not a cheap one, you will see two numbers alongside the element, and these will be symbolized with certain, you're going to have a big number, you're going to have an A there, and you're going to have a Z there, okay?
Yeah.
So the A is simply telling you number of protons and neutrons. The Z is simply telling you the number of protons. So to find the number of neutrons, what would you do if you were given the mass number and the atomic number?
Would you take them away from each other?
Absolutely. So you're absolutely right. We know that Z minus A equals number of neutrons. Okay,
Yeah.
good stuff. And it's good here because this kind of crosses boundaries with chemistry as well. So some of this
Yeah.
material you'd have encountered during your chemistry lessons. Okay, so we're happy with that. We are also, we've looked at a bit of a simulation where we have built an atom. And one of the things we noticed is that obviously some atoms, and in this case, if I go back to my simulation, build an atom, there we go. Okay. If I go back to my simulation, what I
Yeah.
realize is that as I add, yes, another neutron to my hydrogen, what do you notice about it? It becomes unstable.
Unstable.
Absolutely. All right. So what we can generally find out, or what we can generalize from this, and I can carry on building it if you want, and I can put, well, I put another proton. What happens to it if I put another proton in there?
It's
It becomes stable. Absolutely.
Why is that though? Because neutrons have no charge there. So,
Yeah, neutrons have got no charge. Yeah, well, there is a certain balance between protons and neutrons, or a certain ratio that favors the atom to be stable. So remember, like I said, we have a situation in here where positive stuff is in a very small space. So this stuff is repelling one another. The
yeah.
closer these positive things are together, yes,
Yeah.
the greater that force. So if you have neutrons packed in between them, the force of repulsion is not too much. Does that kind of make sense? Sorry, Jay, you froze a little bit. Did you hear
Yes.
that question? Yeah.
Well, yeah.
So what I'm saying is, remember when we looked at that first diagram where we had the protons, and we realized there's a little bit of a problem because positives are in a very small concentrated space because the nucleus is very small. Yeah.
Yeah.
So the closer, so let's just think about this force of attraction. So if I have two positive things, hopefully you can see my hands. When do you think the force of repulsion will be greater? When they are this close or when they're this far apart?
When they're close.
When they're closer, the force will be greater. Absolutely. Okay, the force will be much greater.
Yeah.
Now, think about this space, this empty space, as being packed with neutral stuff, which we're going to call neutrons. So if I have a certain number of neutrons in the nucleus, the force of repulsion is not as great.
Yeah. Yeah.
Yeah. So the
Mhm.
atom will feel a little bit more stable. So for instance, let's look at this diagram. If I keep adding more protons in here, what happens now? There's such a strong repulsion in there that
Yeah.
this is not stable anymore. It needs a neutron to almost space those protons apart.
Oh,
Now,
it's
the moment
space.
I add a neutron in there, you've noticed that it's become stable and I've now got a lithium atom. Yeah.
Yeah, 'cause otherwise they're further away, so they don't repel as much. Yeah.
Correct, because they're further apart, so the repulsion is not as much. So the
Mhm.
neutrons are there. The neutrons actually play a role in the overall stability of an atom. Okay. Now, obviously, this is a simplified model of an atom. Now, can we see atoms, Jay? Are atoms? Do we have technology to be able to see atoms?
We have technology, but not can't see it with your eye.
Yeah, and we actually don't have the technology to be able
Ah,
to visually and physically see an atom.
yeah,
So all these little spheres, these are representation. It's not necessarily that the electron is a spherical shape,
yeah.
but we can see the effects. We're able to make models. So this is just one model of the atom that we're looking at. Later on, we're also going to look at the progression in terms of how the model of the atom has changed over time. Any questions so far?
Nah, I think it's
Okay,
fine. Yeah.
great stuff. So let's just look at this as well. We're still in this simulation. It's quite helpful actually because we can still have another discussion on this. Now, here, what I have created is an ion, isn't it? It says lithium
Yeah.
ion. Now I've got a neutral atom, so I've got a lithium atom. Right. So with the formation of ions, here you will need your, oh, look. So you see, you can see that's the orbit model, by the way. And you've also got what is known as a cloud model. Okay,
Yeah.
so these are slightly different models. So I'm using the orbit model just because it is more visual. It is also known as Niels Bohr or the Bohr model, which I said
Yeah.
we shall look at later. So anyway, back to the question of ions. What do you know about the creation of ions? What can you remember?
Um, what didn't they use like the history of it? Do you mean
No, just how. What is an ion first?
an ion? Isn't it where it's positive, a positive charge? Where there's a positive charge.
So it's positively charged or negatively charged. Okay, so how is an ion created?
Is it when it loses an electron or something? Yeah, it loses an electron, I think.
Yeah, absolutely. So it loses. That's one way of forming. What else can happen to it? So let's
It
just
can
go
gain
to
an
the
electron
next.
as well. It can lose
Yes,
or
so
gain.
you're right. So it either loses or gains an electron. Yeah. So where's my
Yeah.
pen? Trying to find my cursor, getting used to this. Okay, so ions. So we say, oops, an atom that has lost or gained one or more electrons. Okay, so if my atom gains electrons, what kind of charge does it become?
Negative.
Negative, absolutely, and loses electrons, it becomes positive because it's now got a surplus amount of positive charge. So far, so good, no problems there. Yeah.
Yeah.
A key thing I want to note here as well is that when ions, this is something sometimes you're not generally told, but just keep in your mind to say ions are always formed in pairs. Why would we expect ions to be formed in pairs?
Is it so that they balance each other out? Or no, why would they balance each
Yeah,
other
why
out?
would they balance each other? Why do we get ions being formed in pairs? Why can't you just have a positive ion
Um,
existing on its own?
I'm not sure to be fair.
Yeah, okay. So, and that's just down to the chemistry of how the electron behaves. So imagine I have knocked out an electron from an atom, and as you rightly said, Jay, it would become positively charged, wouldn't it? That atom
Yeah.
off which I've taken that electron. Now, that electron I've knocked off, it is not going to stay singly on its own in the air. It will form or join another atom. So that or it'll combine with another atom. Now that atom will end up having excess electrons, making it negatively charged, isn't it? Or making it a negative ion. So
Yeah.
simply because electrons, once knocked off or removed from an atom, cannot exist in their own individual state. They will then combine with another atom. Yes? which then will make that atom negative. So I'll therefore have a positive charge and a negative charge. So there is a law of conservation actually in physics, which we call the law of conservation of charge. The amount of charge we have is fixed, so to speak, okay? And therefore, charge being lost from one is always then gained or moved on to another. A bit like the law of conservation of energy, all right? That is just a law of conservation of charge. And it's always worthwhile remembering or trying to know these laws of physics, because majority of what the whole physics is really composed of is just an application of these laws. And they're not many, to be honest. So all the topics that derive from the laws are quite complex, but the general understanding of these laws is always vital, especially for later studies if you're going to do more advanced physics as well. Okay, so good stuff. So we now understand what ions is. We started off with understanding firstly the makeup of an atom, the internal of the nucleus. Then we also looked at isotopes. We've also looked at notation, which is the AZ notation, which is worth knowing. And we've also looked at ions, and we've also looked a little bit at stability as well. So we're doing good. Okay, right. Now we are going to probe a little bit further into the, where's my cursor? If I can find it. Oh, there we go. There we go. Now we're going to look a little bit into the discovery of nucleus. Let me move. There we go. Sorry, Jay, I just want to move. How do I move this now? I'll put it at the top. Yep. So nucleus discovery. Okay, so this is where we start looking at that timeline I mentioned that led to this so-called the study of atoms or atomic physics, okay? So the new age of physics. So firstly, we'll start off with, well, there was always this idea that from very ancient times, even the Greeks, you know, they always debated to say, to what extent can you fragment something, to, you know, how many times can you cut something into such small pieces, and what would the smallest size be? So there was always this idea of there must be a small particle that makes up matter, yeah, or the bigger sense of matter on a macroscopic level as we know it. All right. So the first discovery, if you like, scientific discovery towards this understanding came firstly in 1896. Okay. So this is just a little bit of history. You're not going to be tested particularly on these, but the models are what I want you to take out of this, because you will be examined on those and not particularly the dates. But in 1896, Henry Becquerel, I can spell that right, okay, discovered radioactivity. All right. And there's a little story that goes with how she discovered radioactivity involving a photographic film. But we're going to look at a little bit more into that when we start looking at radioactivity itself. Okay. All right. So anyway, in 1897, so things are kicking off from in the 1890s. So in 1897, J.J. Thomson, yeah, does that name ring a bell?
Yeah. I do remember doing that in chemistry.
Yeah, he does come up. He does appear in chemistry, and a famous lab in Cambridge is named after him, the J.J. Thomson lab. Okay, because a lot of the experiments were done in there at the time. Anyway, he discovered that when metals are hot, they release negatively charged particles. All right, which he called corpuscles. So at this point in time, if you like, the discovery of the electron was made. Electron discovered. But the full understanding of how the electron fitted in within this picture of the nucleus and the atom was not fully understood, okay? Until in 1904, after lots of experiments, Mr. Thomson, in his wisdom, came up with something known as the plum pudding model, okay?
Yeah.
Now, do you remember anything about the plum pudding model? So this one here, you need to know, because it does I have seen some exam questions worth quite a few marks on this, where you have to compare models. So we'll delve into this into a little bit of detail. So the plum pudding model, what can you remember about that one, Jay?
I think it has a nucleus, I think. And I'm not sure if it has. I'm not sure. I don't know, to be fair. I'm just guessing.
Yeah, no worries. I
I
know you're
remember.
just recalling from memory, which is good. It's absolutely good to try and do that as well without looking at your notes. So this one essentially, because at the time they didn't really know much about the nucleus, so they wouldn't have at this stage been proposing a nucleus in the model. But because they knew about electrons, and they also had this concept of the law of conservation of charge, of things needing to be overall neutral, overall zero, they had this awareness that something in there must be positively charged, because they had the knowledge as well, the same knowledge you have to say negative things do what? They repel when they're in the same space. So you
Yeah.
needed something within that structure to keep it neutral. So they were aware something must be positive. But where it was and its orientation and all that stuff was still unbeknownst to them. So in his model, what he proposed really was, he thought, I don't know what inspired him, whether he was having a cup of tea and so plum pudding cake or something, no idea. But the model goes something like this. If we have a pudding, yeah, this plum
Yeah.
pudding, yeah, you're going to
Mhm.
have little plums in there, aren't you?
Yeah.
As the name says, there we go, those are the plums. Now, these plums, to Mr. Thompson, actually represented electrons, which
Uh-huh.
was a kind of fair sort of observation, because he saw these things being emitted, these electrons being emitted from the surface of metals. So assumed there must be somehow in this bulk. But this bulk itself, in which these electrons lived, was actually, get another different color, was positively charged. Let's try and get, let's go for purple. Yeah, there we go. So the bulk of the pudding was positively charged.
Yeah.
And so these electrons were embedded. So these are the electrons. So the plums, and if I just use an arrow here, might make life easy. So the plums are these blue stuff. And the pudding itself is a different color. We'll go for orange. That's the joy of using a whiteboard. I can use so many different colors. And
Yeah.
the pudding part itself was this bulk that was positively charged. All right.
Yeah.
So that was the first model. And it helped to explain a few things. It helped to explain the observation of the electrons. But it didn't go into explaining everything that we saw. And so there was a lot of work that was still being done. And so in 1909,
Yeah.
Geiger and Marsden performed an experiment.
Mhm.
1909. Oops. Geiger and Marsden. And this was more or less an experiment out of serendipity, because these two students,
Yeah.
their PhD supervisor, or the supervisor, was Ernest Rutherford. Now, Ernest
Mhm.
Rutherford was a student of J.J. Thomson, and J.J. Thomson, for his plum pudding model, got a Nobel Prize. So it's funny how it's funny how you got a Nobel Prize for something that was later on disproved. Because
Yeah.
interestingly enough, actually, it was not just Ernest and Rutherford, but also J.J. Thomson's son, who later on, they also went on to win Nobel Prizes, but having disproved the initial theories. But anyway, away from the history now, looking at what Geiger and Marsden did as students, Ernest Rutherford didn't have much work for them to do research-wise. So he thought, well, I tell you what, why don't you fire some alpha particles, yeah,
Yeah.
positively charged particles, at this at a thin sheet of gold foil, and see
Yeah.
what happens.
So
Because
yeah.
they were all basing it on the plum pudding model, so they had certain expectations if they fired these alpha particles. Now, here I've jumped into radioactivity a little bit, but just to remind you, an alpha particle is a helium nucleus, okay? and it is ejected from atoms or elements or isotopes, more specifically, that are radioactive. Okay, so the idea was bombard this gold foil. If I go to my next sheet here, oops. So the idea was, I'll just draw a little schematic here. You got a little source that produced alpha particles, and this is what is known as it's made out of lead collimator. Now, a collimator is just, if you like, a bore out of this lead, which allows these alpha particles to travel in a straight line so that you don't get them scattering all about. Because if you didn't have this collimator, you'd have them flying all around and you wouldn't be able to direct them at this piece of gold foil. Right? So there we go, my piece of gold foil. And at the end of this gold foil, there was a detector. Now, this detector is really, it was just, sometimes it's also known as a scintillating screen. Okay, scintillating screen made from zinc sulfide. I'm just going to use chemistry here, the chemistry symbol, made from zinc sulfide. So what happens is that if you get an alpha particle pass through and it hits this scintillator, this screen of zinc sulfide, this zinc sulfide fluoresces, it glows anytime an alpha particle hits it. And what they did was they rotated this around this detector, around the foil. Okay, so that's the kind of radius they rotated it around. And what they found was rather startling. And to just share with you, I will go to a new share and see if I can pick out something from here, which will make our life a little bit more alive here. So there we go. So this is, we're looking at the plum pudding model. Hopefully you can see this, yeah?
Yeah.
Okay. Now, the blue dots, J, are the electrons, okay? And the rest of it is just purely protons, or just a positive, it's just a positive charge, all right? So if I fired alpha particles at this gold foil, and that's my gold foil, what would I expect these alpha particles to do according to this plum pudding model? Well, according to the plum pudding model, I would expect, what do you reckon will happen if I fire some alpha particles at that? Well, can you see what happens? These alpha particles, the ones with the 4 dots, they just pass through, don't they? Which is what we'd expect. Why would we expect that? Because the alpha particles are they've got a lot of energy. And there's not much that an electron has got very, very, very small mass. So we would not expect an electron to stop a fast moving alpha particle. A bit like if you put a roll of toilet tissue in front of a cannonball, you do not expect that tissue to reflect or stop that cannonball from firing through it. You agree, right? Exactly what they thought would happen. But when they did it, and lo and behold, this was the experiment they did, the fired alpha particles. Now watch what happens to these little alpha particles, the little purple stuff. What do you see? Now they're not going right through. What do you notice about the path they're taking?
Well, isn't it
By
like
the way, these gray circles are the atom, and that yellow little dot there is the nucleus. So that's just the legend to help you. Yeah, and then the purple stuff, sorry?
They're going straight like through?
They're going straight through, absolutely. So you've got a majority that are going straight through. You're absolutely right. So that was okay. They were happy with that. But what else do you notice though? I could change the model to something that looks like that. So that might be,
repelling.
That might make it a little bit clearer.
Aren't they repelling a bit?
Yeah. So I'm looking, this cluster, this ball here is representing a nucleus of gold in the gold foil. So you can see that a lot of them, as they pass through, or rather, as they approach the atom itself, the gold atom, you've got a lot of them that are repelling it. And if I use this model and just change it to that view, these now are the individual atoms, these different circles. And you can see that if you look at some of the paths, some of these purple little dots are bouncing right back nearly 180 degrees. So just look at this one. Okay, that's 90 degrees. I'm just trying to look at that one, 90 degrees again. I'm looking at one that will probably hit back. And there we go. This one just returned right back. Yeah? You see one that bounces right back. So then notice that majority of the alpha particles went through, which is what they expected. But there were a few that were deflected through large angles, and they couldn't explain that. Why did they get that deflection? Because, as in the words of Rutherford, he said, it was like firing a cannonball at toilet paper and then having that cannonball rebound. That is how extraordinary that event was. So they had to come up with a new model to explain that. So the model, in this case, that Rutherford came up with was in 1911, and he called that the Rutherford model. Now, in this model, to explain why a lot of the alpha particles went through, the conclusion he made, and this is where it's very important because it's the conclusions they ask you about the experiment in your exam questions. The first conclusion he drew was that an atom must be mostly space. Very, very counterintuitive, because if you look at your body or you feel your own skin, you don't feel holes and spaces in you, do you? You feel very compact, very solid. But based off these results, they had to conclude that an atom must be mostly space. And you can notice here that I've got my yellow little nucleus, and around it, I've got this dashed gray line. That is where the first electrons would be. So between the nucleus and where the electrons are first orbiting, there's a huge amount of space. Coming back to that analogy that I gave you with the football pitch and the little peas at the center of the football pitch. That's how far the distance is, okay? So the fact that majority of them went through means an atom is mostly space. Conclusion number one, all right? Conclusion number two. The fact that a minority of them were deflected through huge angles means that, well, the nucleus must have what charge? It must be positively charged. That is why you're getting a repulsion. That explains the huge deflection angles. Now, what I mean by huge deflection angles, okay, and I will try and illustrate this new share on the annotation. So if we go back to this, Jay, where's my, what do I mean by deflection angle? Because you may well be asked to do something like that on an exam. So this alpha particle, when it hits the gold foil, some of them will go that way. Okay, and you had loads that just went right straight through. So the deflection angle is the angle between, so if I draw a dashed line from where, if you like, the alpha particle is centrally aligned,
the degrees.
This here is the deflection angle. Good. Okay. Deflection angle. So for those that bounced right back, the deflection angle is this whole thing.
Huge.
All right. So the only way we would have gotten that big deflection angle, by the way, I'm just going to quickly start writing some of those conclusions because that's where the marks are. Conclusions, atom mostly space. And this is because most alpha particles went through. All right. Now this is conclusion number one. Oops. Conclusion number two. Where's my, oh, there we go. Conclusion two. the core of the atom
Yeah.
must be positively charged. Must be positively charged.
Yeah, for it to repel.
And absolutely, and this is explained by due to huge deflections, due to huge angles of deflection by a few alpha particles. And then the third conclusion, conclusion 3, is that majority of the mass of an atom is contained in the nucleus or core. Okay, so those were the 3 conclusions that they reached based off those observations. And this one generally carries quite a few marks from sort of the previous questions I've seen, exam questions. So it is worth remembering this particular one. It comes up quite a bit, especially that and the plum pudding model. A general type of question would be compare the plum pudding model with Rutherford's model. Okay, so in there you obviously want to highlight the fact that one is only looking at electrons and a positively charged region in which those electrons are contained. So there's no consideration of a nucleus in that one, whereas with Rutherford's model, they have considered that there must be a nucleus, and you also have to also mention some of the findings as well that led to those conclusions. Okay, so you might see a 6 marker on that one. Any questions so far then, Jay?
I think it's fine, yeah.
Okay, good stuff. All right, so this model here, or the actual Rutherford model, these conclusions were made in 1913. So a few years after the experiment itself was done. So the experiment was done in 1909, but the conclusions were only reached in about 1913. So you can see that these developments did take time. Right, then after that came another one. Sorry, my bad. This should say 19. Sorry, not 13, 11. Sorry, 1913 was Bohr's model of the atom. Okay. All right. So there we go. So now we go to Bohr's model of the atom. Now you've encountered Bohr's model in chemistry. Okay. And he proposed this in 1913. No, yeah, 13. So he's the one who owns 1913. Now, the reason why Bohr's model came into play was because Rutherford's model couldn't explain certain things. So, for example, if you have, and this is just a simple demonstration, can I use a simulation? I could probably just explain it. If you have a box, keep that box there like so, and you have, and it's a clear box, and you have hydrogen atoms in here. And you shine some light. Red. So light, and these are hydrogen atoms or molecules, whichever way you want to look at it. Okay. What happens? What emerges out of this? So this is, by the way, white light. White light, to be specific. What emerges if you pass this through a clear glass of hydrogen gas, so to speak, is that then you obtain this side bands missing out of this white light. Now here, I would need, I forgot to put something here, by the way, Jay. I needed to put a prism.
Okay.
I drew a prism here. So you know what the prism will do, isn't it? It's going to disperse. You're going to get colors of the rainbow going into this. So red, orange, up to violet. Yeah,
Yeah.
that's what a prism does. So that's a prism here. What you get on this screen, you find that some of the colors from the rainbow are missing. What's happened to them?
That's in the nucleus.
Yeah. So what has the nucleus of these hydrogen atoms done to that color? What's it done to it?
Has it just blocked it out? Because most of the atom, as we discovered from the first one, is mostly space, and like not like it's open in space, but the nucleus probably blocked it or something.
Yeah, the nucleus probably blocked it out. That could be a possible reasoning.
Yeah.
But also, then there was another thing that was realized, which that's one thought of that's one way of looking at it. But then we have another scenario as well, and the other scenario is where you have hydrogen atoms,
Yeah.
and I pass an electric current through them.
Okay.
If I pass an electric current through, this is just an evacuated tube, evacuated, meaning there are no other atoms other than hydrogen. Okay, so these are my hydrogen atoms. If I pass a current through it, what I realize is that I get these lovely colors being produced in this tube, in this evacuated tube. Why are those colors being produced? Why am I seeing all these different colors? And these colors occur at only particular wavelengths. Now, you remember from learning about waves, did you learn about electromagnetic waves?
I can't. No,
So
I can't
remember learning
think.
about things like radio waves, microwaves, infrared.
Yeah, you did. Yeah.
You did, yes, good,
Yeah.
good. So you know that all those waves had a frequency and they had a wavelength, isn't it?
Yeah.
Absolutely. So hydrogen, when you do this and you pass a current through a tube that's been evacuated and there's only hydrogen in there, it produces colors at particular frequencies that are only typical of hydrogen. If I change the gas and I put helium in here, I'm going to get different colors produced.
Yeah.
If I take another gas like neon and I put it in here as well, I get different colors being produced. So Ernest Rutherford's model couldn't explain why we get the different colors. Why are we getting these different colors? And this is where Bohr's model came into play. All right. Now, in Bohr's model, Bohr said, what must be happening here is we must have a nucleus. Yeah. So that's my nucleus with my protons. Okay. My neutrons. We must have shells in which the electrons live. That was Bohr's, and it's a non-intuitive way of thinking, but nonetheless, at the time, was able to explain things much better than the previous models. So these here are orbits in which the electron would live.
Yeah.
Now, in each of these orbits, an electron can only have a certain amount of energy. And these electrons can jump from one orbit to another. Okay?
Yeah.
And when that happens, we say that the atom is excited because it cannot stay in that state for too long. Okay? Meaning that electron will have to come down. Now, for an electron to move from one orbit to the next orbit, it needs to be given the exact amount of energy that would be needed to go from level 1. Now, in physics, we normally denote this with n numbers. So if this is n equals 1, this particular ring, and this is n equals 2, for an electron to be excited or promoted from n equals 1 to n equals to 2, there is an energy gap that exists there. So unless it has the right amount of energy, it will not be able to go from n equals 1 to n equals 2. Now, there's a number of ways it can get that energy. And one of the ways it can get that energy is by getting that energy from either an electron on the outside, colliding with it, and giving it energy so it bounces off and gets to that level. And what happens in this case, when it bounces to that level, it will drop down eventually. Because remember, it's excited. When it de-excites, it's going to drop down. When it drops down, it's going to release energy. Now, this energy is not in the form, but this energy is going to be what we call a photon. Now, have you heard of the word photon before?
No, no.
Okay. A photon is a packet of energy. Okay. It's a discrete packet of energy. And it's one other thing that you are going to learn about. So you have learned to say that light is waves, but later on, you will come to figure out that light is also a particle. So this particle, which we call a photon, is what you perceive as the light, either green light or blue light. So if the gap here, and each atom will have a specific spacing between n equals 1 and n equals 2. So the energy that it will correspond to when an electron moves from one level to another will be different for each atom. Therefore, the colors that will be produced will also be different. And this instance I've given you, this example of an electron colliding with an electron in an orbit, is what happens in our previous situation when you have this discharge tube. Remember what current is? It's the flow of electrons, isn't it? So these electrons collide with the electrons in the atoms in here, and these excited electrons, when they drop down, they release photons of light, and it is that light that we see. And each atom will be different, will have different energy levels, so we see different colors for different elements, okay? The other scenario of how an electron can get excited, which is now in this case, now we're looking at here, the first top case, oops, gone too far. The top case is if it absorbs a photon of the right amount of energy. So if this photon here, if this photon is absorbed by this electron, and this photon has just got the right amount of energy to go from there to get this electron from n equals 1 to n equals 2, then that electron will do so and jump to that level. But what that means then is that if we had purple light coming through here, at this end now, we will not see any purple light. So let's imagine we're a mixture of colors here because it's a spectrum. So imagine we had purple light and we had green light, okay, green photons. The purple will be absorbed, so I will not see it on the other side. So all I just see is green. And that explains why, in this instance, we lose out on some of the colors, okay? I will try and add more elucidation, and then we can have a quick little short break while you absorb that. But once we finish this, it is the very last element, and then we can go into nuclear radiation. So if I just change my screen share here, let's go here, new share, Rutherford scattering. And let's go back here. And I think I might have to go further back. And let's see if we can find a nice and atomic interactions, balloons and buoyancy. Perhaps not that one. Not that one. Diffusion, double walls. I thought I had it open. J. One moment. I'll try and figure this out. And masses and springs. Models of the hydrogen atom. That might be it. We try that one. And while that's running. So essentially, in summary, the Bohr model, just to conclude, introduced the idea of orbits. It introduced the idea that electrons must be in particular orbits. They can move from one orbit to another. And in that case, we call them an excited atom. But for that
Yeah.
to happen, the need to absorb or the need to be given the right amount of energy. Does that make sense? Yeah.
Yeah. Yeah.
So here we go. So this is a box of hydrogen. All right.
Mm-hmm.
And I've got some white light, which I'm going to be shining. Okay. So that's my box there. Now
Uh-huh.
I click it. That's my white light. Now what you notice, okay,
Uh-huh.
is that if I look at the end of this spectrum, can you see the little yellow dots especially? You're going to see some of the spectrums disappearing. If I show, can I show the spectrometer? If I can show the spectrometer, that might be even better, okay? And I could even
Mm-hmm.
use monochromatic light. So monochromatic light just means light of one frequency. So as I change the type of light I shine, I would see which frequency, which photon. So these blue things, by the way, here, Jay, this is light
Yeah.
behaving as particles. So each of these particles has got a fixed amount of energy. Okay.
Yeah.
Now, as I start moving through the spectrum, I will start noticing that there will be some photons that are going to be missing or absorbed much more greatly than prediction. No, show absorption wavelengths. Okay, so those are my absorption wavelengths. So if I go back here, actually, stand a better chance there now.
Mm-hmm.
Now here, these wavelengths are what the hydrogen is absorbing, these photons. So when
Yeah.
these pass through, the hydrogen is more than happy to gobble them up because it gives them sufficient energy, the electrons, to be able to jump from one orbit to another.
Yeah.
Okay, all right. At that point, Jay, I will allow you to have a little short break. It's been
All right.
knowledge intensive, not very
Yeah.
much on your side. You haven't been doing a lot of calculation. But when we get back, we shall do a few questions and then we'll get into doing some radioactivity. Okay?
All right. Okay. Yeah.
All
Yeah.
right.
All right. Thanks.
Couple minutes, Jay? 2, 3
Yeah. A
minutes?
couple minutes is fine. Yeah.
Couple
All right.
minutes, yeah. I'll see you in about 2 or so minutes, Jay.
Yeah. That's fine. That's fine.
All
That's
right.
fine. Cheers.
See you soon. Cheers. Sorry, Jay, I didn't realize. Oh, sorry.
Ah, it's
Now you can
alright.
hear me. Yeah. So number one. Yeah. Can you see my screen?
Yeah, I can see your screen now. Yeah,
All right. Fantastic. So let's have a go at that multiple choice. We're going to go through some multiple choice stuff just to test understanding of what we've just gone through in the previous session.
yeah.
Okay.
What are nucleons? Are they just like?
Okay. Good question.
Yeah.
And it's something I was meant to add. So nucleons is the name given to protons and neutrons.
Right.
Live
Yeah.
in the nucleus.
Okay. Yeah. So
Okay.
it can't be that one then.
So that's a fancy term. So just keep that in your memory bank, nucleons, okay? So joint term referring to protons or neutrons, not electrons, because they don't live in the nucleus.
Yeah.
Good.
Is it that they must all have one proton in their
Well done,
nucleus?
good man. Because it's the signature, isn't it?
Yeah.
They're all hydrogen, therefore and hydrogen has one proton, so they must
Yeah.
have that. But the
Yeah.
number of neutrons will be different. Okay?
Uh-huh.
Good stuff.
Yeah.
Good understanding there. Okay, next one.
So is
Nuclear
the
number will mean mass number in this case. Okay?
okay. So is the X the symbol,
Well done.
and then A is the I think it's the nucleon number.
Correct.
It's
Well
one of
done. A is the nuclear number.
the,
Good. It's the mass. The number that is also known as the mass number. Good. Well done.
and the Z is the proton number.
Correct. Well done. Okay. So therefore, you have selected A as your answer, isn't it?
Yeah. Oh
Good.
yeah.
Good stuff. All right. Top man.
Atom consists. Is it A, the number of electrons is equal to the number of protons?
Correct. Well done. So far, so good. Okay.
Is the nuclide symbol just that, the 4-2-He? Is that the G? What the
Yes. So
nuclear?
that's the nuclide symbol.
Yeah,
Yeah. So remember where the He would be the element, and
yeah,
the 4 would be the mass number or nucleon number, and the 2 would be the atomic number or the proton number. Atomic
yeah.
number and proton number mean the same thing.
Mm-hmm.
All right, good.
Would it probably be C?
Correct. Well done. Good. Good. It would be C, absolutely. Okay, so 4 easy ones. Should we try and pick some hard ones?
Yeah, yeah.
Okay, good.
Would that just be 14C?
14, correct. Nice one. Wasn't too bad, that one, actually.
Would it just be which one? Nuclide 2 and 4, so D.
Correct. Well done. Good.
Is it D?
D again. Indeed. 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 It is D indeed.
Yeah. Would it be B?
Yep. Spot on the money.
Is it A?
A, absolutely. Absolutely. Okay. They'd use
Yeah.
neutrons. How would they not know what the charge of a nucleus is? All right.
Yeah.
Good.
Mhm.
Good. 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 Good.
Would that be? Wait, so can we pick two then?
Sorry.
Can we pick two then? Because it says statement. Well, because I found two.
It's you can only pick one in this one. Only one.
Oh.
Only one. Only one.
Oh no, then it is B. It's B. I think.
Absolutely B.
Yeah.
Okay. Nucleus is the
Yeah.
total. It's impossible for it to have a total charge of 0. It was
Yeah.
tempting. I think. Were you tempted with A?
No, I was actually tempted with C, but I
B.
remembered that it's actually more a lot of space. I just got mixed up with.
Yeah, and it says would not be correct.
Yeah. Yeah. Yeah.
Okay. Would not be correct. Good. And finally, number 7. Oh no, you can't do number 7 yet. I was going to make you do number 7, but this is to do with once we've done radioactivity. So worry not about number 7. We'll pause on number 7. Okay, great. So we'll move on into our next phase. That was just a quick
Yeah.
summary check on what we had done. Very good.
Yeah.
And now we'll move on. If I go and start a new share, back onto my Active Inspire. Now, I think next time, Jay, I might just opt to use my my normal whiteboard.
Yeah.
Yeah, because it does affect my handwriting a little bit, this board. I've not really used it, but I thought, it's been sitting there, so I might try it and just see how it works out.
Yeah.
Okay, anyway, we're here now, but definitely for next session, so radioactivity. Okay. Who are we? There we go. Radioactivity. So remember we said this thing was discovered in 1896, isn't it?
Yeah.
So way back by Henry Becquerel doing some experiments. She left the key with a photographic film. There was a radioactive source in there. And what she realized was that there was this image, like this photograph, but like this key had been photographed and developed. So there was a shade almost around it, this particular key. And it was later on, due to this, they did a few studies and then realized that something must be emitted, some kind of particles must be emitted
Yeah.
from an element, and this is really how the whole journey of people then doing more experiment and discovering radioactivity came about. Mary Curie as well, who was the lab assistant, or the work together, I should say. She then she went on to do a lot more experiment, discover a lot more radioactive stuff, but in the end it killed her because at that time most people didn't know about the dangers of radioactivity. So normally
Yeah.
when we talk about radioactivity, another term that comes across is nuclear radiation, okay?
Mhm.
So these two are very linked, nuclear radiation and radioactivity,
Yeah.
because radioactivity actually originates in the nucleus. That's where it starts from, in the nucleus. So why are substances radioactive? Why do we have radioactivity?
Um. Is it is it because it's unstable? So
Absolutely, okay? So as a result of instability of the nucleus
yeah.
of isotopes. Remember that experiment we did where we were building atoms, and when we
Yeah.
added a few more neutrons or more protons, we were discovering that sometimes the atom that we built, it was an isotope, but it was not as stable as the original, if you like, atom element that we started building from it.
Yeah.
Yeah, okay, good.
Yeah.
So the
Mhm.
result, the fact that a nucleus is unstable means that one way it can achieve stability is by releasing these radioactive particles, or by emitting particles from its nucleus. Okay,
Yeah.
so emitting
Mhm.
particles, so emitting radiation allows the atom to become stable.
Yeah.
Now, the one thing we say about radioactivity is
Mhm.
that, if I can go to the next page, we say that
So why?
radioactivity, yeah,
Yeah. Oh, so why does the emitting radiation make it stable again? Can you just explain it? Just
okay. So when I talk about emitting radiation, it's more actually meaning to say emitting radioactivity, or it being radioactive is what
yeah.
allows it to be stable. So radioactivity is the phenomenon by which a nucleus will emit one of three or four types of radiation so it can achieve stability. That is what we mean by radioactivity. It is an
Yeah.
activity, okay, just by
Mhm.
the very nature of what we're using. The radio part comes from an element known as radium. Now, radium
Mhm.
is, if you like, one of the first elements that was studied when people were studying radioactivity. And so that's where the word radioactivity came from. But the
Yeah.
activity itself is generated in the nucleus. And the reason why the instability occurs is because that ratio between neutrons and protons is not balanced within those atoms. So there's a
Yeah.
ratio, okay? So this is going a little bit into advanced physics here, but I will try and explain it a little bit here, okay?
Mhm.
Just for your understanding. I think so this is just for understanding. So if I
Yeah.
have number of protons, yeah,
Yeah. Yeah. Mm-hmm.
number of protons here, and number of neutrons here, and I plot
Mm-hmm.
a graph, I'll use my purple. Oops. And I could put some scales here, by the way. So
Yeah.
20, 20, oops, 40, 40. Now, generally, an atom will be stable if it's got about the same number of protons as neutrons. So
Yeah.
this is
Yeah.
like my stability line, this one I've drawn here, okay? So
Yeah.
on this line, everything that is here has got the same number of, so in other words, what I'm saying is on this line, n number of neutrons is equal to p, is equal to the number of protons.
Yeah, yeah.
Okay? But we know that as atoms are built, they're not
Mm-hmm.
all going to follow this line. So as we start adding, what we find actually is that there's a deviation of some heavier elements. Some of them have more protons than
Yeah.
neutrons. Yes?
Mm-hmm.
Now, what happens? So, yeah. So what happens is that for those ones that have more protons than neutrons, what they want to do is they want to lose some of these protons
Yeah.
so that they come down closer to this stability line. Okay?
Yeah. Mm-hmm.
Those elements that have more neutrons, they want to lose some of those neutrons so that they have near enough this ratio of number of neutrons being equal to the number of protons. So it's almost a ratio of 1 to 1, if you look at it.
Yeah.
So the
Mm-hmm.
moment we deviate from this ratio, things start becoming unstable. And is that
Mm-hmm.
instability, so a nucleus is forced to then eject or remove something to balance and bring back that ratio. That's why it's being radioactive.
Yeah.
Yeah, does that kind of answer your question?
Yeah. So,
Okay, good.
yeah.
So you'd never really be asked that question, but at A level, yes, you would. So it's a good question just to kind of enhance your understanding. So it's a very good
Yeah.
question in that respect. So these particles or these radioactive elements rather can become stable in one of three ways. Okay,
Yeah.
four ways strictly speaking. So types of emission. Oops. You have alpha radiation.
Yeah.
You remember any other ones?
Beta,
Yeah, beta.
beta, sorry,
Yeah.
radiation.
Any
And
other one?
then ionizing.
Okay, you're remembering some keywords there. Another one is gamma radiation.
Oh yeah, gamma ray. Yeah, I forgot about that one. Yeah.
And another one, you don't really need to worry about so much. I've not seen exam questions come on it, but it's neutron emission.
Yeah, I don't think we did that. Yeah.
Yeah, not a lot of people do this one. It's not examined a lot. It has been mentioned in your syllabus, so I thought just worth you knowing about it. Okay.
Yeah.
So alpha radiation, so remember all these originate in the nucleus. Let's just be clear. All of this stuff is in nucleus.
Yeah. Mm-hmm.
It's not happening outside the nucleus.
Yeah.
All right, if I can write that, nucleus. Good. So let's just look at what these types of radiation are. Or before that even, I want to make a note because you asked me a question and then I lost my train of thought a little bit. I want to make a little note here just about the
Yeah.
nature of radioactivity very quickly for completeness sake. We say that radioactivity, come on, it's a random process. It's a random and spontaneous process.
Yeah.
What do we mean by it's a random process?
So you can't predict it. It just randomly
You can't
happens.
predict exactly when it's going to happen.
Yeah.
Yeah? Spontaneous, it will happen
Mean.
when it needs to happen. It's not affected by temperature, not
Yeah.
affected by pressure, not
Uh-huh.
affected by any chemical processes around
Yeah.
it. Okay?
Yeah.
So
Mhm.
that's one key thing to note because at times you will be asked, what do we mean by radioactivity being random and spontaneous? So these are some little keywords you will want to take note of
Yeah.
and remember about that nature of radioactivity. All right, good stuff. Now I'm just going to go quickly into this arena here now, where we're talking about the different types of emission. So what is alpha radiation? When we talk about alpha radiation, what is it really? Well, an alpha particle is
Mhm.
simply a helium nucleus. That's what it is.
Yeah.
Helium nucleus. And it's given
Mhm.
the symbol alpha from the Greek letter. And a
Yeah.
helium nucleus can be represented as, and it's worth remembering this notation, 4, 2, H, oh, come on, H, E. Okay, let's move my finger there. Better. Okay, so 42HE, or sometimes it is given the notation 42 with an alpha. All this is representation of an alpha particle. So this is a particle. What about a beta? What about beta radiation? What is it comprised of? What is it exactly?
What do you remember?
Not to worry. It's just a fast-moving electron.
Oh, yeah.
And it's given the symbol 0 minus 1 beta, or 0 minus 1 with the electron symbol. Okay? So the first two we've looked at, these are particles. Gamma radiation, on the other hand, this is just electromagnetic waves. So this is not a particle. Neutron emission occurs if an isotope has got a lot of lots of neutrons in it, and this is just a neutron. So for example, if I had this isotope of helium, it's not very stable. So it can achieve stability so it forms a much more stable helium atom and releases a neutron. Okay, so that is what we mean by neutron emission. Now, in the case of beta radiation, it's a tricky one because we've just said that all this happens in the nucleus. How can you have a fast-moving electron ejected from the nucleus? How's that possible? What was it doing in the nucleus in the first place?
Is it sort of taken from the outside of the, like a normal electron on the orbiting? It says sort of taken from there.
No, not quite actually, because all radiation happens within the nucleus. It doesn't happen outside of the nucleus. So it can't take anything from the outside. It has to be something that is created from within inside. And what happens in beta radiation, okay, in this case actually, is that normally this isotope will have so many neutrons in it. So if it's got a lot more neutrons than protons, and that ratio of 1-to-1 or near 1-to-1 has been disturbed, then what happens is that a neutron in the nucleus turns into a proton. A neutron turns into a proton, but it also produces an electron in that process.
How does it do that? It's because 1-to-1 ratio.
Yeah, so because imagine let's just imagine a nucleus where you've got, say, 2 protons, and I've got 1, 2, 3, 4 neutrons. Now this is not very happy as it is. There are more neutrons than protons. So it wants to establish that balance. So what would happen in this case is that a neutron here is going to turn into a proton. So let's take this neutron. It turns into a proton. So now I've got 1, 2, 3 protons, and I've got 1, 2, 3 neutrons. But in the process, it also produces this electron. But this electron cannot live in the nucleus. So what happens to it? It is ejected with high speed. And that is what we call beta radiation. Now, I'm taking a little bit of an extension here. Now, according to the conservation of charge, which is a big thing in physics and chemistry, what's the charge of a neutron?
Neutral, no charge.
0. Good. What's the charge of a proton?
1+.
Good. +1. What's the charge of an electron?
-1.
-1. Now, if this was an equation, this would be the left-hand side, and this side here would be the right-hand side. What do you notice about the charges?
Can you just explain how the electron is formed? Because I sort of get it, but I sort of don't in a way.
Can I explain how come again with that question, sorry, Jay?
Like how you just went over it, how the electron is made
Yeah,
inside the nucleus
yes.
form. Yeah,
So because it's very unstable, the
yeah,
mechanism that the nucleus undergoes through is this mechanism where it takes one of the neutrons, because remember that example, we had 4 neutrons and we had 2 protons.
yeah,
Yeah. So one of the neutrons decided to become a proton.
yeah,
But in so doing, it can't just produce a proton and end there. Because if it did end there, Jay, then what you'd
yeah.
have a neutron turning into a proton. Now let's look at the charges. What's the charge of a neutron? 0.
Neutral.
What's the
Yeah.
charge of a proton?
Plus one.
+1. Now this has violated the law of conservation of energy.
Yeah.
If I have 0 charge on my left-hand side of the equation, I must have 0 charge on my right-hand side of the equation. In the
Yeah.
same way when you're writing ionic equations in chemistry, you're using that law of conservation of charge. You always, can you remember writing ionic equations? And always looking at the charge on the
Yeah, yeah,
left-hand side and the right-hand side and making sure they're equal.
yeah.
Yeah. So the only way it can balance is if
Yeah.
on this side, I also have something with a -1. And what is that thing that we know that has a -1 charge?
You have an electron to balance it out.
Absolutely. So an
Okay, yeah.
electron, so just by knowing these equations, even before we were able to study beta radiation perfectly, by using this law of conservation of charge, we're able to determine that a neutron must turn into a proton and an electron. And
Yeah,
it is this electron that cannot live in the nucleus, so it's ejected, and we call that beta radiation.
Yeah, I get it now, yeah.
Okay? The
Yeah.
other atoms that have got more protons than neutrons. Now those, what they do, Jay, is, you probably thought about this, the proton turns into a neutron. So now this side I've got a +1 charge, but it also turns into something else because the neutron has got what? 0 charge. So I need something with what kind of charge?
You need a positive charge.
You're
No,
absolutely
yeah,
right.
positive.
I need something with a positive charge. And that thing is known as a positron. It's an electron with a positive charge.
Yeah.
Don't worry. Now that's advanced physics. Just keep that in
Yeah.
your mind. That's just advanced physics. That's just for your own knowledge to know. At this rate, all you need to know is that when a neutron turns into a proton, it also gives off an electron. Don't worry
Yeah.
about the proton part because now we're getting into the world of annihilation and Star Wars and antimatter meeting matter, because a positron is antimatter of an electron. And if you combine the two, you get pure energy and annihilation. So I'm not going to get into all that exciting stuff, but at least you understand that this law of conservation of charge plays a big part in deciding what is formed when something splits or changes into something else.
Yeah.
Yeah, good
Yeah.
stuff.
Yeah.
So we know now the beta radiation is a fast moving electron. A neutron turns into a proton because the isotope or the nucleus of that isotope is rich in neutrons and has more neutrons than protons. So it tries to reduce the number of neutrons by increasing the number of protons. In gamma radiation, it's just electromagnetic waves that are produced. So a nucleus becomes more stable because by giving off electromagnetic waves, it reduces the amount of energy in it, inside the nucleus. By reducing the amount of energy inside the nucleus, that nucleus becomes a bit more stable. Now you ask me, how does something become more stable? By losing energy. Are you able to explain that? Why would something become more stable by losing energy?
Is it by giving up an electron or something?
No, in gamma radiation, so all these here, by the way, Jay, all these two, alpha and beta, all these are particles. Whereas this here is a wave. This is not a particle.
So
this here is a particle as well, by the way.
Yeah.
So how would something become more stable by giving off electromagnetic waves? or energy by giving out energy?
Um,
Let's think of an analogy maybe to help understand what's going on a little bit here, because these are very abstract areas and they can be tricky for that reason, in that we can't really see what's happening in an electron. So sometimes you do have to have a bit of an imagination to find out what's going on. So here we go, Jay. I've got two balls, okay? And this is my ground level. And I've got another ball here. Which one do you think is more stable, ball 1 or ball 2?
Ball 2.
Correct. What would ball 1 need to do so that it can be as stable as ball 2?
Fall down, maybe?
Absolutely, you're right.
Yeah.
It needs to fall down. When it falls down, have it lost or transferred a certain store of energy?
Yeah, because it's moved, so kinetic, probably.
Okay, kinetic, but there's something else that has reduced. Gravitational potential, well done, which is given by mgh.
Yeah.
Here it had mgh because it was at a high value of height there. Whereas here the height is 0, so m times g times h, which is 0, gives you 0. So what does it have to do for it to become more stable? It has lost
the gravitation.
Absolutely, it's lost that gravitational potential energy. The same thing happens to a nucleus of an atom. When it emits gamma radiation, it is like this ball falling down to a lower ground. It fills and becomes more stable.
Yeah.
Okay, so that's the analogy there to just help guide you why gamma radiation occurs. Okay, so we've now looked at the different types. The other thing that we need to look at is what you mentioned now, Jay, which is a very important aspect of this topic, and that is this idea of ionization. Now, one of the key properties of all radioactive materials, so all radioactive emissions are ionizing. All of them. Now, what do we mean by ionizing? What do they do?
Is it the decay bit?
Not quite. So what do we talk about? What are ions, by the way? Remember that definition we had of ions?
It's where an atom has lost or gained an electron.
Correct. So what we mean by when we say that they have got this ionizing ability is that they have the ability to knock off electrons off atoms.
Yeah.
And remember we said that ions are always formed in pairs? Yeah? So when they knock off electrons from one atom, that atom becomes positively charged, but those electrons that have been knocked off join another atom, which becomes negatively charged.
Yeah.
So they create pairs of ions, all of them. That is because they knock electrons off atoms.
Yeah.
So all forms of radioactivity are ionizing. Another thing as well, Jay, is that if you have a source of radiation, say, I don't know, I've got some isotope of polonium or uranium, and it's releasing radioactivity. Oftentimes, it won't just release one type. It will release some alpha, it will also release some beta, and it will also release some gamma.
Yeah.
But there'll be one that it will primarily produce. So don't just think of it as one element only produces one type. They generally come in a varied number of forms within that particular isotope. Okay? So all radioactive emissions are ionizing, so they knock electrons off atoms. Okay? And that is what actually makes them dangerous to humans. Now, we can look at the ionizing capability of each of those forms of radioactivity because it's something that you will be tested on. So if I look at alpha particles are heavily ionizing. Why do you think alpha particles are heavily ionizing? meaning they lock off electrons from atoms in the air, so heavily ionizing.
Is it because
Ionizing. So of all these forms that we've looked at here, Jay, these three different types. Go back. Oops. No, too far back. This here, alpha particle, can you see is a helium nucleus? Which of these is the largest, is the biggest?
the alpha one.
Absolutely. That's a nucleus. That's just an electron. That's electromagnetic waves. That's just a neutron. Yeah. So it is the biggest. So it's a bit like having a rugby player, big guy, run through a little crowded area. He will create a lot of displacement compared to if you get somebody who's slim and slender to run through the same crowd of people.
Yeah.
So it's the same concept. So alpha particles are heavily ionizing. Yes?
Yeah.
But they only travel for they have a very short range. So I might just use this. Okay. So short range. But they only travel for about short range in air, for about 5 centimeters. And they can be stopped by a piece of paper or by hand. Yeah?
Yeah.
But they are the most ionizing because of their size. And can I annotate that? Most ionizing. Yes, I can. Beta radiation, which is the fast-moving electron, this is also ionizing, but I can say medium ionizing, because it's just an electron that's moving very fast. So it's not gonna knock off a lot of other electrons on its way. And also because beta has actually got a long range in air, long range, it dissipates its energy over a large distance, long range, okay, and can be stopped by few millimeters of aluminium, okay? So it's stopped by few millimeters of aluminium, whereas gamma radiation, this here is the least ionizing, because it's just waves, least ionizing. And it's got the largest range of all of them. And actually to stop gamma, you need some thick layers of lead, okay?
Yeah.
So stopped.
But how can the
by thick lead. Go on.
How can the gamma one be? Do you know how it's electromagnetic waves? How can it even be ionizing at all? Because
very good question, Jay. That's a very, very good question. Jay, oops. I'm just gonna close this door here.
Yeah.
Yes, Jay. So we're back to this. Yes, very good question to say, how can it even have any form of ionizing capability?
Yeah.
If it is a very good question. And remember the concept where I said waves can exist as particles and particles as waves. You will learn that in later physics. Actually, it's a little bit advanced, but quite advanced physics. Now, you won't believe this, but if I told you that you are a wave, would you believe that?
No.
Yeah, you are a wave. So am I.
Yeah.
But at the same time, you're also a particle. But depending on the circumstances, you can behave like a wave. But those circumstances are very, very hard to put in place so you can actually see yourself behaving as a wave. So for electromagnetic radiation, it can also behave as a particle. Now that's the realm of quantum physics. Very, very fascinating realm. So what happens is that these waves actually behave as particles and they are absorbed. So it is that excitation. So if I go back, I'm going to go back quite a bit here. I'm going to use my mouse, make my life easy. If I go back to that original diagram where we looked at, here we go. Didn't even have to go very far, actually. So if we look at this diagram now, don't know what's going on there. Remember where we had a look at electrons jumping from one level to another?
Yeah.
We said that if they absorb a photon, now a photon is a packet of energy, and if it's the right amount of energy, they can jump from one energy level to another. Do you remember that? Yes?
Yeah, yeah.
I'm trying to find the diagram. I did find it, and then I lost it. Should find it somewhere around here, I think. After this, presumably. Yes. And I've got a better diagram to go with it. Here. So if you have a photon, so this is what gamma does essentially. It comes in as photons. Now, imagine now you are the outside electron. If this electron is given sufficient energy, it can actually escape from the entire atom. And that is what causes that ionization. But you're right, that won't happen as easily as the ionization caused by alpha or beta. So gamma radiation, the amount of ionization is very, very minimal.
Yeah.
But when one ion is formed, okay, when one ion is formed, this
Yeah.
ion that's now formed can go on to create other ions. So that is how it kind of creates ions, because now this is now an ion. It will go on and start colliding with other particles and may steal an electron from them, then creating another ion. So that's how gamma does it. But it's very, very minimal. It's a very good question. But the only reason is because we have to think of gamma as behaving as particles when it creates ionization. Okay? You'll never ever be asked that question in your exam to say, even though gamma are waves, why do they cause ionization? You'll never ever be asked that. But it's good for your own understanding as well. So far, so good?
Yeah, yeah.
Excellent. Right. So touched on ionization, and we have looked at, we've looked at the range of some of these. I don't know what that is. 1, 2, 3 express form. Nope, not using that. So, where's my, yeah, there we go. Okay. So the next part now that we're gonna look at, can I move this from here? Don't know what I've done here, Jay, but I've ended up with, oh, do I close that? Yeah, good. So we've looked at the ionization properties. The next thing we're gonna look at also is the equations that go with the different types of radioactivity. Do you remember doing decay equations, Jay?
No.
Really? So if I have an element and it loses an alpha particle, so let me call this element X, and I'm going to use my notation here, which is A and Z. An element X loses an alpha particle or emits. It's going to form a new element. Are you happy with that? It's going to form a new element, which I'm going to call Y. Now, this new element is going to have a new atomic number. How do I work out the atomic number of this new element?
Do you take away the 4 and 2?
Absolutely. So firstly, the mass number is going to be A minus 4. So whatever this A was, subtract 4 for it. And Z minus 2.
Yeah.
And that is how you write decay equations. You can, of course, Jay, rewrite this differently. Think about this as an equation where this arrow sign means the equal to sign. So now you know you have, like any equation, you have a left-hand side.
Yeah.
And you have, and you have a right-hand side. Okay? So I can rewrite this equation as well like this. AZ X equals A minus 4, Z minus 2, minus 4, forming Y. I can take this here to the other side of the equation, and guess what? It's going to be a plus because it's a minus here, so you can rewrite that as plus 4 to alpha. Okay?
Yeah.
All those forms acceptable. So this represents alpha decay. So that's for alpha decay. What about for beta? And we've got to remember these equations. Okay, I can put numbers in there, but I've kind of already made it clear to say just remember to subtract whatever the numbers are. Z minus 2, which is here, A minus 4, which is there. Okay, and again here, if I balance everything out, it's balanced. A minus 4 plus 4 gives me A. Z minus 2 plus 2 gives me Z, which is on the left-hand side. Yep, good.
Yeah.
Now we move on to beta decay, because this is another equation you need to know. For beta decay, again, if I start off with my X, A, Z, and I lose a beta particle, now beta, you need to memorize this, is 0 minus 1. You can either use an E here, or you can use the beta symbol. The new element that's going to be formed, J, to find its atomic number and mass number, well, A minus 0 gives you what? Is just A. Z minus 1. What does that give you? Z plus 1. Good. So beta decay increases the atomic number, but leaves the mass number unchanged. Okay? And this will be for beta decay. Now, in the case of gamma, well, there's no change because it's just energy that's released. So in the case of gamma, you just have X, A, Z, released as a gamma, which is 0, 0. So the new thing that's formed is still going to be AZX, just with a lot less energy. That's all. Okay? And this would be for gamma, gamma decay. All right? So that's all the decays with the associated equations that we need to know. And we can always look at a few questions, exam questions, to check understanding on that one. Oops, didn't mean to go back. Forward. Right, so now that's done, the next thing we're going to do is look at detecting the particles. How do we detect the particles? How do we detect radioactive particles?
Well, would it be when you can't really tell if an atom has really lost an
yes, very hard to tell, you're right. So what we use is we use something known as a GM tube. Okay? In full, it's known as a Geiger Muller tube. So what a Geiger Muller tube does really, Jay, is so if you've got your radioactive source, radioactive source emitting radioactivity, it's going to ionize the air. It's going to ionize the air molecules.
So it's going
now, because the air molecules are ionized, it means they're charged.
Because it's going to take all, gain all.
Absolutely. And what this Geiger counter is, it measures the charged, how many charged air molecules are there at a time.
Oh, I get it. So it's going to charge it first, and it's going to see how many are uncharged at the end.
Almost, but not quite there. So what you normally do, if you've got a Geiger Muller tube, is you have your source of radioactivity in a collimator so that the radioactivity can come out in a straight direction. Okay? And then you have your Geiger counter. Now, when this radiation enters, there's a thin mica screen. It's like a thin little paper. This is to allow alpha particles to pass through, because if it was not very thin, then alpha would be blocked, so you'd not be able to detect it. So it's a very thin paper. So imagine an alpha particle goes inside here. Now here, the air molecules, what the alpha particle is going to do is that it's going to knock off electrons from these air particles which are in the tube. Okay? Now this tube is so designed that it is able to accelerate or move these charged particles. So just, and this is a very rough schematic, this is just to make it more illustrative. So it's going to have, let's imagine a top blue side that's going to be positively charged, and a negative side here at the bottom. When these
Yeah.
alpha particles create a positive ion, the positive ion is going to be attracted to which side? To the negative charged thing, isn't it?
Mm-hmm.
And a negative ion that the alpha particle creates is going to be attracted to what?
The positive
The
side.
positive.
Mm-hmm.
So it measures how many charged ions it is receiving to know the level of radioactivity that is taking place. That is how a
Yeah.
Geiger tube works.
Mm-hmm.
Okay?
But I thought it ionizes the air molecules outside though.
No, it doesn't ionize the air molecules outside. It ionizes the molecules inside the tube.
Yeah. So it puts a charge on them
Absolutely.
and which way they go to.
Which way?
Measure.
So remember we said that ions are always formed in pairs.
Yeah. Uh-huh.
So
Yeah.
when this alpha particle gets in here, it's going to form positive
Yeah.
and negative ions.
Mm-hmm.
So the negative ions are going to go to the positive plate.
Oh yeah, because it's gonna attract it.
Absolutely. And the positive ions are going to go to the negative plate. Now,
Yeah.
because ions are moving and ions are charged, remember
Yeah.
what is the definition we have for current? Current is the rate of flow of
Yeah.
charge.
I'll charge. Yeah.
Good. So because there is charge that is flowing to these
Mm-hmm.
plates, there's going to be a current that is going to
Yeah.
be generated. So this
Mm-hmm.
Geiger-Müller measures the current that is being produced. And from the current, we're able to know how much of the air inside has been ionized.
Yeah. Okay.
If a huge current is generated, that means there's so many ions. That means that whatever it is we're looking at is highly ionizing.
Mhm. Yeah.
So if I brought an alpha source and brought a beta source, the alpha source will create a huge current on my Geiger,
Yeah.
whereas
Because
a
it's got.
beta
Yeah.
will create a very small current because it's not as ionizing.
Uh-huh.
And gamma will produce an even tinier current.
Yeah. Uh-huh.
Okay,
Yeah.
good. So that is one way we detect radioactive particles. Another way we detect them is by using a photographic film, like Henry
Mm-hmm.
Becquerel, or
Yeah.
another way we use is by using something known as a gold leaf electroscope. Gold leaf electroscope.
Yeah.
Now, the gold leaf electroscope, what you have is you have a zinc plate there, like so, and then you have a stem, and then you have a gold leaf.
Mm-hmm.
Now, you can charge these gold leaves. So imagine I had a charged gold leaf,
Yeah.
and I charged it and I made it positively charged. So all this is positive. Now, the leaf here, can you see has separated away from the stem
Yeah.
because
Yeah.
they're all positively charged.
Uh-huh.
If I bring a radioactive source next to it, the radioactive source is going to ionize the air around it. So what is it going to produce? It's going to produce, I use blue, negative ions.
Yeah.
Let me write, negative ions. And it's also going to produce positive ions.
Yeah.
So what do you reckon is going to happen? Well,
Those. Yeah. They're gonna
negative
attract.
ions will be attracted to these positive ions. And what's going to
Yeah.
happen? It's going to neutralize the charge. So when you bring a radioactive source next to a charged gold leaf electroscope, well, what you then expect to see is that the electroscope leaf is neutralized
Yeah.
because all radioactivity is ionizing. So that is another way you detect radioactivity. You either use a gold leaf electroscope or you can use a Geiger-Müller tube, a GM tube,
Yeah.
or a photographic film. Or there are other methods as well which you can use, which you don't have to worry so much, but worth just remembering if you want to. You can use something known as a bubble chamber. I'm not going to go into so much the details of this,
Yeah.
but that's another method of detecting it. Okay?
Yeah.
Bubble
Okay.
chamber essentially has lots of bubbles in it, and you shine a radioactive source, and then it creates an ionizing trail. And it's the
Yeah.
ionizing trail that you then look at. in simplistic terms. Okay, so that is
Yeah.
detection. We've also, looking at time, yeah, I'm going to have to add on a little bit more time there. Gold leaf electroscope. So we've looked at detection. The next thing that we can add on to that is then just the dangers of radioactivity. So what do you think some of the dangers are?
Well, if you like, can it make you a bit deformed and that?
Yeah, and like asking this in your exam. So because of, okay, it's ionizing, therefore can damage cells,
Yeah.
can damage nuclear,
Wait, why can it damage the cells?
because your cells are made of atoms,
Yeah, oh, and then
and
it
your
takes.
atoms have electrons around them. So if it knocks electrons from the atoms that make up your cell
Yeah.
is essentially left charged with ions in it.
Oh, okay.
Okay,
Okay. Yeah.
and that may disturb nuclear material, especially DNA. So when the
Oh,
DNA then replicates to make new cells, it can't make them as healthy or functioning to the right functionality as before.
yeah. Okay.
So the key word you should never say is that it kills cells. Okay, so you say it damages, can damage cell nuclear material, living cell, be more specific, living cell nuclear material, and tissue. So when you have, well, alpha particles are not as penetrating, but when they encounter your skin, it's as if they leave almost like a little bullet hole in your cell.
Yeah.
Okay. On the other hand, because they're not as ionizing, if you ingest or you drink it accidentally, it's going to create some severe damage to the immediate tissue, but it's not going to penetrate so far into the deep tissue. Beta, however, even though it's not as ionizing, it can penetrate far greater depth. But because it's got such a huge range, it loses a lot of its energy. And because it's not as ionizing, it doesn't do as much damage to your body.
Yeah.
Okay? Gamma rays, again, similar arguments. But the key thing is that you don't want to be overexposed to high levels of radiation. Okay?
Yeah.
So there's something known as, two terms you will come across here: irradiation and contamination. What is the difference between these two words?
Isn't contamination when you contaminate it with something, so like it's a mix of something?
Yeah, so well, with irradiation, this is just exposure to radioactivity.
And then
So if I have a
contamination.
radioactive source and I'm around it, I'm being irradiated. But contamination is not exposure. Contamination is like, now I go and have a cup of tea. I didn't realize that instead of a sugar cube, I've actually put a radioactive material and I've drunk it. So now I'm contaminated because I've got amounts contained in bulk of body, in the bulk of body. So irradiation is not as dangerous as contamination. Contamination oftentimes is lethal. For irradiation to be lethal, you have to be exposed to high doses of radiation.
Yeah.
Which now brings me to this interesting topic, because we are being irradiated as we speak, and that is because of something known as background radiation. So we can never escape from it. So what is background radiation? So it's the radiation that exists all around us, and we cannot, and we cannot shield ourselves from it. So what are the sources? Any ideas?
Would it just be maybe
Sun.
Oh yeah, I was gonna say
Rays.
this. Look, yeah, I was gonna say that, but I was thinking
Yeah,
probably.
that's a good one. Just remember that one, Jay.
Yeah.
Another one as well is rocks.
Rock.
Yeah, the rocks over which the houses are. Okay, the
Yeah.
granite rocks. They produce a gas known as radon, and radon is radioactive. Another thing
Yeah.
is the food we eat is also radioactive. It's got carbon
Yeah.
in there. All living
Right.
things have got something known as carbon 14,
Mm-hmm.
all living things. And
Mm-hmm.
carbon 14 is radioactive. So as I'm speaking, you and me are releasing radioactivity, are producing radioactivity. When we eat our food, no matter how organic, no matter how clean, it has some traces of background radiation in there of carbon 14.
Yeah.
So we can't shield ourselves from that.
Then
However,
don't. Yeah.
yeah, go on.
Don't you, when you eat, you get contaminated with it though?
We get contaminated, but it's very, very low doses. They can't particularly do us any harm. It's when
Okay.
the doses become really, really high. Now, when you look at doses are measured in sieverts.
Mm-hmm.
Okay, so
Yeah.
doses measured in SV. Oops.
Yeah.
Okay, so you
Mm-hmm.
see that notation sieverts. Now, it's normally millisieverts. So background radiation is of the range of about 10 millisieverts, and we can survive that. That's okay, even through
Mm-hmm.
the food. The moment we get to about 1,000 millisieverts,
Yeah.
it starts getting severe. We will get ill, but our tissue can be repaired from it.
Yeah.
So in cases like Fukushima, where they had that nuclear explosion, yeah,
Yeah. Yeah.
what they were receiving was a moderate dose. So
Mm-hmm.
people will, of course, get sick in the long term. Then
Mm-hmm.
now you have very high doses, which are of the range of 4,000 millisieverts. Now that's
Mm-hmm.
very, very high. And at that level, it will kill you. And we
Yeah.
don't really push ourselves through that, apart from, say, people during, when the atomic bomb was dropped and during Chernobyl, those who were very, very close to that bomb received about
Yeah.
4,000 millisieverts. At that point, I mean, your gut, all your intestines, everything inside has been severely destroyed. It's very hard to recover from that.
Yeah.
It's death. Death is ultimate. Okay?
Mm-hmm.
So
Yeah.
we only expose ourselves to about 10 millisieverts, which is not a lot. So we can actually survive that. Okay?
Yeah.
Okay. Now, the
Yeah.
next part of this, and it's a very, very last part of it, is going to
Yeah.
be looking at half-life. But
Yeah.
I can see that we have run out of time, so I
Mm-hmm.
won't pursue that. But the next session we do have on physics, I'll pick up on it. It shouldn't take us
Yeah.
more than 15 or so minutes to complete. All right.
Yeah. Yeah.
Okay. So,
Yeah.
Jay, do you have, I need to make sure it's AQA you're doing for your sciences, isn't it?
AQ, yeah. I got it on right down my book, yeah.
Great,
AQ.
great stuff.
Mm-hmm.
Okay. So what I'll do, Jay, is just trying to think what I could do now, how we could do this. Because it's not yet quite a complete topic.
Yeah.
I won't go further than this. I'm not setting any homework per se.
Oh yeah,
Uh,
I've done the maths one, by the way.
Oh, good, good,
Yeah,
good, good.
that question that
Yeah, you can. There's a way you can do. You can actually just send me a screenshot of it if you want, if you're able to
just in
project it, or you can project it and then I can take a shot of it and then I'll have a look at it and then we can review that.
so should I just project it and then screenshot
Yeah,
it?
yeah, yeah. Go for it.
Alright.
Oh, I see why it's hard to project because you got the Liverpool virtual background, haven't you?
Oh,
Well, I'll tell you what you can do, Jay. Do you want
yeah.
to take a picture of it with your phone?
Send it on WhatsApp.
And then send it to me via WhatsApp, and then I'll look at it. And if there's any problems, we'll touch on that at our next math session.
Yeah.
Yeah,
Yeah.
great stuff, Jay. So no homework for today, Jay. Relax for the rest of this afternoon.
Yeah.
Go over the video if you feel you need to go over any areas. And next time, I think I'll probably stick to using the visualizer. It just means
Yeah.
I need to use, I suppose, more board markers and stuff like that,
Yeah.
but it doesn't matter. I did find it a little bit not as smooth transferring from
Yeah.
one screen to another, and then not being able to fully write my letters as I normally would if I were using a paper. So
Yeah.
tomorrow, I think I will probably use the board. What do you prefer, though? The whiteboard, or is it better with the? Do you prefer me using this Active Inspire software, or do you prefer the whiteboard?
Probably maybe the whiteboard, but yeah,
Yeah, we're
probably.
together. We're together. It's much smoother, no? And my work is much neater as well, because this was
Yeah.
very, very difficult for me to go
Yeah.
through. Good stuff. Right. So Jay,
How do you save the
tomorrow.
video? Sorry.
Sorry.
How do you save the video?
It should, once we finish the meeting, it should
Oh,
give
it
me.
says yeah, it will be converted to MP4 when the meeting ends.
Yeah.
Yeah.
So once we finish, we should have that. Any
Yeah.
questions for me, Jay?
Nice. Good. Thanks. Yeah, I'm
Good
good.
stuff. Okay. So
Uh,
tomorrow, just having a look at what we provided on the timeline. Let me just get. Oh, where's my gallery? Let me have a look at this. Okay, we can touch on some chemistry, definitely. Now, mostly in your chemistry, Jay, you said, hang on, I don't think I haven't made a lot of. You said you were mostly doing revision, isn't it? Mostly going through stuff you'd already covered
yeah,
in year 8
revision,
and
yeah.
stuff like that.
Yeah, the
Periodic
last topic
table.
we did was probably that the syllabus topic was changes to the Earth's atmosphere, which we'd already done.
Yeah, which we'd already done.
Yeah.
Would there be any particular topics then that you might want to? I'll let you lead this one. Is there any particular topic that you might want to start off with that you think
In,
you might benefit from in
in
tomorrow's session?
chemistry, shall I just get?
Yeah, of course.
I wouldn't. I'm not quite sure, but I wouldn't mind doing because I haven't done this before. So
Okay.
organic chemistry or something like that. I haven't done it.
Yeah,
So
yeah. Why not? Why not? We can do some
yeah.
organic chemistry. Organic chemistry is fun. Cool. All right. We'll pick up on organic chemistry, and I'll throw in a few of the elements of what we've already covered, just to keep you abreast of previous knowledge and things like that.
Yeah.
So we'll start off with looking at organic chemistry, because you will start doing it in year 10 anyway. So might as well get a
Yeah.
step ahead.
All right, that's good. Yeah, that's fine.
Nice one. Right, Jay. I will see you tomorrow, and
Yeah.
let me know if you have any problems with the video, and then I can send you mine. But hopefully, it should all be straightforward. Yeah.
Oh yeah, it should be fine. Yeah. All right.
Nice one.
Thank you.
Catch you
Thanks.
soon.
Yeah.
Oh, good,
See
Jay.
ya.
Have a good afternoon. See you
Cheers.
tomorrow.
Cheers.
Bye. All right.